Bismillah ar-Rahman ar-Rahim. Dear students, today we're going to learn about the tree data structure. Okay, we have learned arrays. We saw the linked list and a lot of more things, their implementations and all, queues and stacks and all. But today this tree data structure is something which has something of both worlds. That is something of the array and also something of the linked list. It combines basically the advantages of an ordered array and as well as linked list. Ordered array, the searching is very fast. You can go for a binary search on an ordered array, but insertion and deletions are going to be costly in an array. But here the insertion deletion in the linked list are faster. Okay, so the tree actually combines the advantages of both. It has a great searching, faster searching you can do on it, and as well as it has a better way of insertion and deletion like linked lists. Okay, so it has got both these things. So why we actually need a tree? It's faster than linear data structures for sure, and it's more natural fit for some kind of data. For example, we've got a hierarchical data. If I talk about say for example myself, Junaid, and I'm gonna do some teachings, and I got some research, and I got some activities to do where we can have sports activities or whatever. Okay, so for this kind of data, okay, the tree structure is more natural fit. Okay, we have on the top some node called root, and then we got to have a subtrees. So what is typically firstly the definition of our tree? Now look at the definition of a tree. It is a set of one or more nodes. Okay, it's a set, because we have got a lot of nodes here. It can be a set of all these nodes, and we need to have these conditions. We need to have a root node, okay, and from which is the parent of all, which has no parent, and it has children but it doesn't have a parent. It's a root. Okay, the remaining nodes are partitioned into n disjoint sets. The important thing is, if we have other nodes, they're gonna have their own kind of sets. If for example I cut this arrow here and here and here, they become separate trees with B as a root, C as a root, and D as a root. Okay, so they got to be partitioned into disjoint sets. Say for instance, this is T1, this is T2, and T3 and so on. Okay, so this is a tree because we got a set of all these nodes, and important thing is we got a 3 disjoint sets. Okay, if it can be partitioned into that. If we see this as a tree, we can't say this is a tree, because if B and E, this arrow, if you see, you can't make them as a separate sets here, so that doesn't satisfy this condition second. Okay, so this is not a tree, even though we can partition, we can have this itself is a set of all these nodes. Okay, but it can't be partitioned into disjoint sets, so we can't say this is a tree. So its subsets need to be themselves trees and so on. Okay, so this definition is kind of recursive. What we say with the root and its subsets, they are also applicable to the subsets as well. So D is either an empty, means we don't have any node, or consists of node R, the root. Okay, this is my root, and possibly empty set of trees. There could be empty set of trees, there were no tree at all. Subsets. Okay, that means the R, the root, does not have any child. That's also possible. That's also a tree, but it can have many disjoint sets of subtrees. Okay, attached with the root. And okay, that this is why this is recursive, because that's applicable to the B also now. So for example, this part disappears, the B should be like the tree itself. and that is applicable to any node we talk about. Okay, either it does not have a, like a C, it doesn't have any node attached to it. Okay, so or if it has, then they should behave like a disjoint subtrees. One more thing, in natural in nature we have trees, okay, but the trees basically have the roots on the bottom, and then we have, say for example, the branch going on, and then we have the leaves on the top. But here something is, upside down. The root is on the top and the leaves are on the bottom. These are leaves. Okay, so there are let's talk about the terminology of the tree. Okay, so if you see here, we may have root, the parent, child, sibling, external, internal nodes, subtrees, ancestors, descendants. Then there is a height, depth, a lot of things. Let's talk about those things. Okay, we got the root, the top element, that is a root. Okay, this guy is a root. Okay, and except root, each element has a parent. If we talk about any internal node, they have the parent. Say for example, this level they have the parent, the root. Then this level they have these as the parents. Okay, and so on. And each element has 0 or more children. You can have a 0. Remember that. That means if you have a if the tree, there is no node, then tree is empty. If there is a single node, then that's a root. It may have 0 or more children. Okay, it can have more children, whatever you can attach with them. Okay, you can have 0 or more children, not a problem. Then we will limit those also. For example, binary tree and all, we'll see them later on. And here the nodes, other than the leaves are someone which don't have their which doesn't have any children. Okay, they are not parent of any child, so they're called children. They're called leaves, sorry. So this is a leaf, for example, this guy is a leaf, this is a leaf, this is a leaf, this one, this one, this one, and all other nodes are internal. So so the nodes can be either the internal nodes or the external nodes. The external nodes are called the leaves. Say for example, here we have we talk about this node. Say this is the node T. Okay, now this is its parent, this is the grandparent, and this is its grandparent. So what we are technically saying are these are the ancestors. We can also say these are the ancestors of the node T. Similarly, if we say the downside, they are the descendants of the T. Okay, these guys are the descendants. So we have the term descendants of T, node T, and these are the ancestors on the upside. It's as simple as it is. Okay. Yeah, you should remember, I repeat, that if there is no node, that is again a tree, what we call as an empty tree. Okay, and these guys, for example this one, this is a subtree. Okay, even if I say take this whole thing together, this is a subtree. This is subtree. So subtrees attached with the node. Now there can be subtrees attached with this node, a subtree attached with, say for this node, this is the subtree itself, and so on. Now if you look here, we have a term called path and path length. Okay, so what is a path and what is a path length? So into this, okay, whatever. So if we want to find the path from A to the H, we are seeing how many edges are there. Okay, so 1, 2, and 3. So this is the path length. Okay, the number of edges in the path, A to B, B to F, F to H. So this is what the path is, simple as. Now we have the term called node level, and we have also the depth. Depth or level, we see. So this is the level, particular level. This is another level. This is level 0. This is level 1. This is level 2. This is level 3, and so on. And the depth also is that path length. Okay, so for example, it doesn't have any one above, so its depth is 0. so technically whatever the level is, that's going to be the depth of that particular node in that level. Okay, so D is on a level 1, so its depth is 1. And we can also say in the other way that if D is a parent of G, D has a depth of 1, G is going to be 1 plus 1, that is 2. Simple as it is. Okay. And also these on a level, the nodes on the same level are called siblings. Okay, they're called siblings, and but they are siblings because they belong to the same parent as well. Now these are on the same level, but these two are the siblings. Okay, because they belong to the same parent. Children of same parent, siblings. So height of a tree. That's the longest path length from the root to the leaf. So for example, here we say E, it is at 0, 1, 2 level, but it doesn't tell us about the height, because we have to see which one is the longest. So I see this path which go from this way, A to H, is the longest of which has a depth of 3, and this will reflect the height of a tree. Okay, now depth belongs to the particular node and height belongs to the tree. Now a degree, the maximum number of possible children for every node in the tree. Okay, say for example, we say, hey, you can have a possible number of children, you can have a 3. Okay, now that's going to be degree, but we see like this. Say for example, it has the 3 children. Now this has only 2, this has none, and this has, say for example, 3. Now what we are saying is that you can have at the max 3 children. Okay, so even though this is a 2 only, the maximum of this tree, this node has 3. Say it has 4, for example, the maximum is now 4. So the degree of which is the highest is the degree of a tree. Okay, a maximum of possible children for that particular node in the tree. Now we say some tree as a proper tree or a full tree. If we specify its degree, say for example we are specifying for example 3 as a degree. So let's talk about this diagram. Okay, now you may have either the 3 children or you don't have any children. So okay, nodes have all the children non-wide, that means you're gonna have a 3, or all children are wide, that you don't have any children. Say we have specified that our degree gonna be 3, so we say take up the root node. Okay, it has 3 children, A, B, C, for example. Now A has 3 children, D, E, F, and C has 3 children, G, H, and I, and B have no children. So it can be either wide or it satisfies the full degree. Okay, then it's called as a proper tree or full tree. Okay, so what is the height of this tree? Height is 1, 2, 3. So height is gonna be, will the height be 2 or 3? It's got to be 2. Why? Because we start from the 0. So we say 0, 1, and 2, or this way 0, 1, and 2. So height is 2 and degree is 3. Now what are the types of trees? Okay, if we talk of generally, every node can have any number of subtrees. There is no maximum limit. Okay, so different number is possible of each node. Like we say that we have, say for example, it has attached 3 guys with it. Now this is attaching 3 guys, this may attach 4 guys with it, and so on. And so there is no limit typically. Okay, then we say n-array trees, where we actually limit the degree of a particular tree. Okay, so we say every node has at most n subtrees, so put up a limit on that. You cannot have more than n when we specify n. So for example, in a very special case, we have a binary tree where n is 2. That means you can have either 0, 1, or at the max you can have 2 nodes attached to a particular node. Okay, now a subtree may be empty. Okay, that means there's nothing attached with it. That's what I'm saying, 0. That means its pointer is wide, or it can attach 1, or it may attach the 2 at the max 2. So that's why I call it an array. Say for example, we got 3 array tree, where at the max we have a 3 subtrees or subnodes attached or children attached like this guy, so where the degree is 3. Okay, you can't have more than 3. Okay, you can have lesser than 3. Say for example here we had 3, here 3, there is none. Or you could attach, say for example 2 or 1 or 0, but not more than 3. Same is with the 4 array, 5 array, and so on. And we will take a very special case as a separate video, that is a binary tree. Now we have an ordered trees. This is the n array, which have an upper limit of degree, but have one additional constraint. What is that? The ordering is imposed between the parent and its children. You know, the ordering can be like less than, equal to, greater than, equal to, or greater than. Okay, what does that mean? Let's take an example. Say for example we have an n array case, and we can have any many keys. Okay, and say for example we got a key, say for example we got a key like 5, we got then 10, then we say 15, and we say 20, or you can have any many keys. Now if there is a subnode attached to it with this key, okay, it got to be lesser than 5. Okay, it got to be all less than 5. And here this is something, all nodes which are greater than 5 and less than 10. Okay, so all keys belong to that. And here similarly we can have less, greater than 10 and less than 15, and so on. Okay, like here less than, greater than 15 and less than 20, and you can have any many keys. And then we have special cases for these ordered n-array trees, like we have what's called as a binary search tree. Okay, because it's a binary, we talk about these later on in detail. Though n is gonna be 2, that means the upper limit is 2. You can't have more than 2 children. And you have like this, that if you want to have something here that's got to be less than the parent, so say for example it is say 20, so whatever is on the left side is going to be less than 20. So if say for example you want to enter 10, well, it's going to be on the left. If you want to enter 25, it's going to be on the right, and then so on and so forth. Okay, so that means whatever is greater than, less than 10 is going to be here. Whatever is greater than 10 but less than 20 is going to be on this side. Say for example 15. On this side, say for example 5. And same is the case with this 25. Say for example 30 will go here, and we have what is called as, say for example 22 will go here. Okay, greater than 20, that is 22, but less than 25 on this side. So this is called a binary search tree. It's very helpful in you know, like arrays. We say that we can apply the binary search for the better search. So we can have a binary search tree, which we'll talk later on why we need them. Okay, then we have other also ordered trees, like we have heap, which we talk about later on in a separate video. We also have concepts of like a balanced tree, which depends upon a type of a tree, which we talk about later on. And we should first, I think, take in next video in detail the binary tree. Okay, the most famous one, the binary tree. That will be in the next video. Until then, ma salama. Okay.